Hello, this is Tyler Beamer. This is an instructional video for Math 130 College Algebra. This video is in regards to Chapter 6, Section 4, Logarithmic Functions. Logarithms are inverses of exponential functions, and we use them simultaneously back and forth to help us to solve both exponential equations and logarithmic equations, and that's kind of where we're headed with all of this content. So here's the definition of a logarithmic function. Just like an exponential function, logarithms can have different types of bases. So the base of a logarithm is this sub notation here. It's denoted by a in this general formula, but there will be a number there, and a will need to be greater than 0 and not equal to 1. And then, so this is the base of the logarithm. X is the value that you're taking the logarithm of, and then y is what it's equivalent to. We can rewrite logarithms into exponential functions using this model. So if y equals log base a of x, then x, I'll rewrite this so you guys can see that a little better, which is what you're taking the logarithm of, is equal to a to the y Let me just rewrite this completely so you guys can see better. So essentially what the logarithm is equal to is the exponent. The base stays the same in both the exponential and the logarithm, and then what you're taking the log of is what a to the y is equal to. So if we have either this information or this information, we can essentially go back and forth between the two. So that's what we're going to be working on in this particular section. So let's take a look at working through some examples so you guys have plenty to use as a reference. So this is an exponential notation, right? So it's in this notation here, and I'm trying to write this into a logarithmic notation. So I'm essentially trying to go from the x equals a to the y equals log base a of x. So notice that the exponent is what my logarithm is equal to. So I'm going to do 2 equals, so that's the y, if you're following along with the format up here. The log base and the exponential base are the same, so that's going to be a 3. And then what the exponential is equal to is what I'm taking the log of, so that the 9 goes there. Okay. So then over here we would have 2 equals log base 4 of 16. Okay. Over here we would have 2 equals log base a of 1.6. And then over here we would have 3 equals log base a of 2.1. So those are some examples of how you can go from exponential to logarithms. Okay. And then we want to go the other direction as well. So we pretty much do the reverse of what we just did. So notice down here I've got logarithmic functions, and I want to write them as exponential functions. Okay. So notice that the log base and the exponential base are going to be the same. So that's going to be my exponential base. The logarithm is equal to the exponent, and that should be equal to what I'm taking the log of. So log base 2 of 8 equals 3 is equivalent in exponential form to 2 to the third equals 8. And you should be able to actually check that and make sure that's equivalent. So 2 to the third power is indeed equal to 8. So it's kind of hard, well, we hadn't really talked about it yet, how to actually compute these logarithms. We're going to here in just a second. But down here, you can actually do that on your calculator. All right. 18 would be 3 to the negative 2 equals 1/9. All right, so remember that we can rewrite this negative exponent as 1 over 3 squared, which is indeed equal to 1/9. Okay. These would be a to the 6th equals 3. Okay. And so if we wanted to solve for a there, we would take the 6th root of 3. Okay. And we'll get into solving some of these logarithmic equations here in the next section. So that's kind of a little bit of foreshadowing. All right. And then 20 would be b squared equals 4. So then if we took the square root of 4, that would be 2. So we could also solve for b there as well. All right, so that's how we go back and forth between logarithms and exponentials. Okay, so we're following this format up here. Okay. All right, so now we want to be able to actually find the value of logarithms, and our calculator will do that for us. So we can use that to check it. It says to actually find it without a calculator in these directions, so we'll do both. We'll actually find it with the rewriting, and then we'll check it with our calculator so you'll know how to do both ways. So if I want to find the value of this, I'm basically saying this is equal to x. It's equal to some unknown, right? And I'm solving for x. So now I'm essentially doing what I just did up here, right? I am rewriting this in exponential form. So this is 2 to the x power equals 1. And so if we think about what that would be, we know that anything raised to the 0 power equals 1. So I know that x would equal 0 in that case. Okay. And then I could check myself on my calculator. So let me zoom out some. So you have log button here on the calculator. It's right below x squared. So there's the log button. So if we click on the log button, it will do common log, which is base 10. Okay, and so I can do this a couple of different ways. If I have a newer calculator, I can do alpha window. So let me go back and do that. So alpha window, so the green button window, and then I have 5 log base. I'm going to hit enter there, and it actually gives me the opportunity to find the logarithm of any base other than base 10. So that's nice. So I could actually put in log base 2 of 1 directly and hit enter, and notice that that's equal to 0. Okay. If you have an older calculator, what you have to do is what we call change of base. You have to do everything in base 10. So if we wanted to do this, doing change of base, I would find the common log of 1 and divide that by the common log of 2. So common log is base 10. So if I just hit the log button, it automatically does base 10. And so that's what we call change of base. And it's always the common log of this value divided by the common log of the base. And notice that we get 0 in both cases. So if you have a newer calculator, I'd use that shortcut using the alpha window. If you have an older calculator, you'll probably have to do this change of base. So, but I'll show you some other examples here so you can get good at that. Alright, so let's look at, going the wrong way, log base 8 of 8. Okay, so that would be, equal to x. We're trying to find x, so 8 to the x power equals 8. So obviously that value of x would have to be equal to 1. Okay, so then alpha window, trying to get this glare off of here, alpha window number 5, so log base 8 of 8 is equal to 1. If I'm doing change of base, it's log 8, common log 8 divided by common log 8, which is also 1. Alright. 27, so log base 5 of 25 equals x. So what is that? So 5 to the x equals 25. Put that in exponential notation. So then you could probably recognize that x has to equal 2 there. Alright, so we could double check that on our calculator. Alpha window 5 log base 5 of 25 is 2. Common log of 25 divided by common log of 5 should also be 2. So either way. Alright, and then last but not least, 28. So equals x, so 3 to the x equals 1/9. So x would have to be negative 2. So that this would be, the negative exponent would go to the denominator to turn positive. Right, so that's where the 1/9 comes into play. And so we could check that as well. So alpha window 5. So what was it? Log base 3 of 1/9. So 3 of 1/9 is negative 2. Alright, if you're on the old school calculator, common log 1/9 divided by common log of 3 should also give you negative 2. Sorry about the glare here. Alright. So that's how we go back and forth between exponential and logarithmic functions. We'll be using this quite a bit to solve logarithmic equations and exponential equations. And those two functions are inverses of each other, and that's really primarily what we use them for. Of course, there are applications of logarithms as well. All right, so we talked about the natural number e in the last section. So now we're going to talk about the natural logarithm function. And essentially, that is the inverse of base e. And so natural logarithm function is denoted by the symbol ln. So ln and e are inverses of each other. And we can go back and forth between the logarithmic notation and the exponential notation following this setup here. Okay. And then we already talked a little bit about this, but common log is base 10. So if you don't see a base with your logarithm, you assume that it's base 10. And that's a common log. And so you can go back and forth between those two using these ideas. Okay, similar to what we did up here. So let's take a look at some of these examples. So we're actually solving some logarithmic equations here. Some pretty basic ones. We'll get into solving some more difficult ones later on. And you guys have these notes on Blackboard, so you can pull this up if you're having a hard time seeing the small print. And I'll write them out again. But essentially, to solve a logarithmic equation, we rewrite into exponentials. To solve an exponential, we rewrite into logarithms. So if we want to solve this for x, we would rewrite it into exponentials. So 3 squared equals x. So then x would be equal to 9. And then you could check that on the calculator like I just showed you. So essentially, log base 3 of 9 should equal 2. And it does. So you can check yourself using those methods. Alright. So 88 is like 87. The solutions for these are on Blackboard. But in an effort to keep this video a little shorter, I'm just going to do the odd ones here. So 89, log base 2 of 2x plus 1 equals 3. So rewrite that. 2 to the third equals 2x plus 1. So rewrite that as an exponential. 2 cubed is 8. And then I can solve for x, so minus 1, divide by 2. So 7/2 would be the value of x. Okay. Let's see, 91. So log base x of 4 equals 2. So rewrite that. So x squared equals 4. So if I square root that, x would be 2. And I'm using only the positive root because that base for your logarithm has to be positive. So it's got to be greater than 0. So I'm only using the positive root there. Okay. And then 93 ln of e of x equals 5. So remember, ln and e are inverses, so essentially these guys just cancel. And I'm left with x equals 5. Alright, so that should get you started on solving some really basic equations that we've talked about. And we'll look at solving some more challenging ones in the next section. Alright, so here's an application problem. I wanted to do the one about alcohol and driving. So 133. So it says the concentration of alcohol in a person's bloodstream is measurable. Suppose that the relative risk R of having an accident while driving a car can be bottled by an equation of the form R equals e to the kx, where x is the percent of concentration of alcohol in the bloodstream and k is a constant. So suppose that the concentration of alcohol in the bloodstream is 0.03. So that would be x. So 0.03% results in a relative risk of an accident of 1.4. Find the constant k. Alright, so we are going to put 1.4 in for R. We're going to put 0.03 in for x. And then we're solving for k. So this is solving a exponential equation. So we're going to use logarithms to do that. So I'm going to do the ln, since I've got an e here, and those are inverses. I'm going to do ln of both sides. Got to do it to both sides because it's an equation, and I got to keep it balanced. Ln and e cancel, so that just gives me 0.03k. And so then if I divide ln of 1.4 by 0.03, that'll give me the value for k. And so I could use my calculator to do that. So ln, the natural log, is right here. So it's right below log, so ln. So ln of 1.4 divided by 0.03, and that gives me a k value of 11.2157. Okay. And then the next question, B, says using this value of k, what's the relative risk if the concentration is 0.17%? So then we're finding R. So putting 0.17 in for x, we have now the value for k. So I want to basically figure out what this is equal to. And so I'm going to plug that into my calculator. So your calculator is your friend for these problems. So remember where to find E, that's second ln. So then it is 11.2157 times 0.17. And so that's 6.73. Okay. They don't really tell us what the scale is on this, but I'm assuming if you have a blood concentration of 0.17, there's lots of risk. That's pretty high. That's what, double the legal limit. So using the same value of K, what concentration of alcohol corresponds to a relative risk of 100? So they're just switching up the variables here. So giving you R, and you're solving for X. So then we would once again do ln of both sides. So take the natural log. Ln and E are inverses, so they cancel. Divide ln of 100 by 11.2157. And so 0.4106. So that's obviously a huge concentration of alcohol. I don't know what the amount of alcohol in the bloodstream is where you die by alcohol poisoning, but I don't know. You're probably approaching it if it's 0.4106, I'm assuming. I'm not really sure. D says, if the law asserts that anyone with the relative risk of having an accident of 5 or more should not have driving privileges, at what alcohol concentration in the bloodstream should a driver be arrested and charged with a DUI? Okay. So let me organize this. So this is D. So then basically we want to find the alcohol concentration that goes with the risk of 5. So we put 5 in for R. We use the value of K that we found earlier, solve for X. So once again, do ln of both sides. So ln of 5 divided by 11.2157. So that would be 0.1434, which is certainly above 0.08. So obviously allowing more risk in that case. And E, we won't do E since I don't know what example 10 is. That's in the book. But this will give you an example of how to, use logarithmic equations with E, solve logarithmic equations with E using ln and E simultaneously. Also, hopefully it gives you some perspective in the fact that, don't drink and drive. Lots of risk involved. So, all right. So hopefully this helps clear up any questions you have. If you do have any, please email me. The homework for this section will be posted to Blackboard. So once again, email me if you have any questions in regards to those. Thank you. Have a great day.